my mic? How about now? Okay. So last class we had a introductory class. Example, we had talked about definition point of view. What is the definition of additive manufacturing, also called 3D printing? So if you see that this term additive and then 3D printing, interchangeably people actually use it. Say example, when it comes to academia, you may find a lot of time you heard 3D printing, but when it comes to industry, right, people actually use a lot of or most of the time additive. So when technology was started, as I mentioned, it was more of a prototype, and then eventually it was functional part printing, so on, right? So when it comes to industry, right, they don't like to use when you are using a part in functional application, or when you are using a part or component, so they don't like to call prototype, right? So that's why they actually changed the terminology. Instead of 3D printing, they actually adapted additive, right? Since you actually layers materials, which is opposite to the subtractive manufacturing, where you actually remove the material, right? So that's how you'll actually find these terms. But when it comes to the principal point of view, like when it comes to the technology, right, working principle is same, with respect to any technology that we actually talk about it. So this is the overview or what exactly the technology, how technology works. So if you see that initially you may have different methods to capture the data or to create a CAD file, like which is a 3-dimensional. So sometimes you can actually use a different CAD softwares. Sometimes you can use a 3D scanning, or sometimes you can use a manual method to draw and then you actually convert into 3-dimensional software, use a 3-dimensional software to create a 3-dimensional object, right? So once you actually create the 3-dimensional object, then you need to actually convert into STL file. So why we need to convert? I think I actually talked about in the last class that we need to have a simplified version of a 3-dimensional model, right? Or also simplified not just in terms of model, but also the data size, right? And also you need to actually have the flexibility in terms of handling the data, right? So STL file actually will give you the flexibility in terms of handling the data, especially when you want to see that the size of the data, right? Since it has only the surface information, right? So whatever the 3-dimensional that you have the file, it will convert into surface information, which is again you actually use a triangle the representation for representing an entire model. So why we need to actually use a triangle representation? Mainly, so if you see any other representation, so you will not be able to actually represent finest component or the finest part, right? Especially example, you have complex structure like a sphere, right? So if you actually use a triangles, you can actually capture entire sphere, right? If not, in a larger, triangles, but you actually decrease the size of the triangles, so you'll be able to actually capture or represent the entire model. And sometimes you may have complex structures where, so if, other than if you, I think people even tried different other representation, like example, square, and then they have cubes and different other methods, but at some point they felt the triangles actually is more accurate in terms of capturing or converting your 3-dimensional model into more of a representation, right? So and then as you know that machine only will understand G code, right? Which means you may be having a STL file. That doesn't mean that you can straight away actually print a component, right? You need to have the sliced version of it where you actually slice the model and you actually combine in terms of corners, and then you actually stretch it. Like when you actually stitch the corners, and then you actually form this one layer. So to actually transfer it, the machine only will understand the G code language. So there we need to actually have that format where machine can actually understand, right? So that is one part of the software where you actually process the file. But other part of the machine, like basically you need to have the machine ready, right, before you actually set it up, right, before you actually print. Like example, putting right material, and then temperature, or different environment, etc. So you need to actually keep your machine ready, right? And similarly, what kind of build plate, and then what is the condition of the build plate, and so on. Of course, you can actually control some of the process parameters. Like example, what is the temperature that you actually need to maintain inside the chamber, or what is the condition of a nozzle temperature, and then bed temperature, right? And then you can actually make sure that your machine is actually ready before you actually print, right? So and then you actually print the component, and then you may be required to add sometime a support structure, or sometime you don't need to add the support structure, right? So there you need to actually see exactly how much support structure you need, and so on, right? And then most of the time you can actually use whatever the component that you actually manufactured or the fabricated. But there are cases like you need to actually go for post processing, right? So there we actually go for further post processing in terms of heat treatment, or in terms of machining, or especially to enhance the printed part, both surface finishing and then properties of the printed component, right? So if you see that, I mean, there are dozens of technologies today, right? Although the technology was actually started with one or two, but you will see that today there are dozens of variants that you will actually find. But in 2012, AISTM, the committee, classified the technology based on the way that work in terms of energy, or in terms of material fusion, and then in terms of how can categorize, so that this can actually fall under one umbrella. So, right, example, VAT photopolymerization is as being the first 3D printing started. Like example, I talked about SLA, right? That is actually comes under VAT photopolymerization, where so they actually try to cure, or the whatever the liquid material that you have. Like imagine initially you have a resin, right? And then you need to actually solidify, right? And then you actually fuse them, right? And so that you can actually form the layer, right? So and then whatever the variants in terms of you are spreading the resin, and then you are selectively fusing it, right? Selectively you are actually fusing it and forming the layer. So those all the technology actually comes under photopolymerization. You are actually trying to cure the using a different maybe laser, right? Based on the different polymer chains, right? So that's why they call it as a VAT photopolymerization. So and then you have another technology which is material jetting, which is nothing but imagine you have you are spreading the resin through the nozzle, right? It is like nothing but inkjet printer, right? You have the inkjet like you have the multiple jets come through the jets, and then they were actually trying to push the material like in the form of a droplets, right? And then that droplets you are actually spreading on the bed, right? And then selectively you are actually multiple tiny uh, solidify the actually going through popular technology, and then this is second technology that after in terms of polymer, so after SLA process, where if you see that all the technologies, desktop-based technology or desktop-based 3D printers are actually fall under material extrusion. So the binder jetting is another technology where you think about like you are actually spreading the powder or spreading the polymer powder, right? And then now you are actually you put the binding material, right? And then you actually put the binding material selective region wherever you want to actually form the layer, right? So the binder actually will help forming the bond between the powder, right? And then you actually go for a post processing, and then you actually go for a further metallurgy, powder metallurgy concepts, and then you actually fuse them, right? So here they don't actually use any example the way we use laser or UV light, etc. Here simply use the binder material, and then you actually bind the powder together and then form the layer, right? So and then these are the actually four classification in terms of polymer, where you can actually print polymer materials or but when it comes to metal, you will not be able to actually directly print. But of course, there is some progress they made when it comes to the material extrusion, where so they have actually infused the metal, or even you can actually prepare the metal filament, and then you can actually extrude, and then you get the metal component, right? But when it comes to other four variants, where binder jetting, powder bed fusion, and then sheet lamination, and then directed energy deposition. So these are the actually metal-based additive manufacturing. Here, when it comes to, you can also actually make a polymer-based when you actually use the polymer powders, and then you use a different binder material for binding them together. So and powder bed, and then sheet lamination, and then directed energy deposition are, I think if you see that today, 80% of the metal actually are used by powder bed fusion technologies. Especially you think about like you have already decided what kind of a material that you want to actually print. So you are not much interested in actually going for multi material or combining. Of course, you can also actually combine the different materials, but and then think about like you have already decided, example, titanium implants, right? So now I know that I need a titanium for printing implants. Now I have the product, and I have a design ready. I have also decided exactly what kind of material that I want to use it, right? So it is like more of a product, technology, right? And then you can have a series of a product that you can actually manufacture, because you're trying to, print one material, and then you're trying to see the product coming out of it, right? With a single material, or maybe you can actually combine the different powders, but you'll be able to get, the component, which is like a more of making a, the product with maybe single material or combined, composition. But when you want to actually vary the, composition gradually, or vary the form a different alloys within the structure, so that may be a little difficult when it comes to the powder bed fusion. And the other technology is actually the other popular technology is the directed energy deposition. So here, unlike where powder bed fusion, where you actually spread the huge amount of a powder, and then you actually selectively melt or selectively fuse the area, right? But here you only add how much ever material that you need to actually add, because the powder is actually coming from the nozzle, right? So here the powder is actually spreaded before even a laser pass through it, right? But here the laser actually will be passing before the powder being deposited. So it is basically you are trying to fuse them as and when you actually add the powder, right? So which means the amount of the material that you actually required for making a component will be, how much ever you need, that much is enough in this case. But here it is you need a lot of material, because imagine you have the bed area is like 200 by 200, right, mm. right? In this case, every time you need to actually spread that much of amount of material, like in that area. But whereas in this case, so you don't need to actually spread, right? Because the powder actually comes from through the nozzle, which is and this laser is actually coming in the middle. But of course, there are variants. But again, you're only trying to fuse the material as soon as you actually put the powder on the substrate, and then the laser will come and then fuse directly, right? So this is another technology where we actually talk about using a different sheets, like instead of powder or instead of filaments. So they actually use the sheets, and then think about like you're actually placing the sheet after sheet. Maybe you have a different thickness, right? And then you actually selectively remove or cut the different profiles. And then you need to have the strong bonding between the two sheets, right? So that's where the sheet lamination. I will go through the individual technologies in the later class. So now let's, I think, talk a little bit about material extrusion. So this technology is not something very new for us, actually. This is, if you see that a lot of our technologies. Example, how many of you actually seen the making a jalebi, right? So how the jalebi is actually formed, right? And then you might have actually seen the forming the shape using the different ropes, right? Think about you are actually putting the rope one after another one, and then what you do is you try to use a different gluing methods so that you can actually stitch them together and then form a three-dimensional object, right? So similarly, if you want to make any jalebi, what you do is you actually use the extruder, and then you actually push. Of course, we also do manually. This is our motion, right? So and then you have the basically the cloth we'll be using, and then you're putting the raw material, and then you're trying to push the material, right? So that is where you are actually trying to push the material, right? So think about now if I actually make it more, automate this process, right? If I actually convert entire the process into more of automatic, right? So that is how actually material the extrusion works actually. So history, I think I will not go spend more time, as I think we have already discussed in the previous class that this was actually the third, the technology, and the second when it comes to the polymer-based technology, right? Where you actually see that extensively people use, for making a component. As I said, first being stereolithography, and then second most widely adapted and used because it is quick and in terms of making the component. So of course there are different names when it comes to the technology, right? Example, fused filament, and then plastic jet printing, and then material extrusion, so on. The reason being, as I mentioned in the last class, when you have a technology, when you actually start, and then you may be having a trademark, and then you may be having a patent. So sometimes patent may get expired, but still you may have the trademark with you, right? So that's why still FDM actually, name was actually used by the statisticians because they are the one to invent this technology, and then till today they only use all the rights in terms of names, etc. So as I said, this patent are no more valid now. Anybody can actually use the technology, and then they can actually print. But again, like I said, when the moment the patent were expired, then you could see that lot of price drop. So when I bought a first printer in 2011, it costed us almost like 25 lakhs, simple desktop 3D printer. But today, I'll be able to buy for 12,000 or even 10,000. I think students can make it even below 7 or 8,000, right? So when you have all the component, that's how the technology today. Of course, when it comes to the component precision or the properties may vary, but at least you'll be able to build the printer for a lower price and so on. right? Especially when you see that a lot of revolution that actually happened when it comes to this technology, open version, like example RepRap and then so on, and then example do it yourself and so on, right? When you actually allow this kind of activities, and then you will find more affordable. So why this technology actually important, right? Why people so uses this often, right? So this technology within the AIM, as I mentioned, now we have a lot of areas people uses this technology. So I think the reason being, if you see that hardware part, right, it is very simple, and then when it comes to the cost, mainly you need a motors, the stepper motors, and then software. And nowadays all the softwares are actually available, and then most of the softwares are actually open versions, right? You can just plug in, and then you can actually convert all the your stepper motors, like completely automate, right? So of course, a lot of them are users of especially prototyping and functional part, and then so on. Nowadays, people are actually expanding the technology. Example, composite 3D printing, and then 4D printing, and so on, right? So when you actually have that flexibility in terms of making the component with varied materials, and then adding extra material, then you can see that you can expand the technology into different fields where you need a lot of material. So if you actually see that the common, when it comes to the technology, right? If you see that across, there are different variants when it comes to the material extrusion. But if you see that commonly uses these terms, right? One is FDM, and then another one is FFF, which is like fused filament fabrication. As I mentioned, if you want to start your own company, you will not be able to use FDM name, and because it's trademark with standards. So the core characteristics of this technology are like example, you have the solid filament. Sometimes you have the pellets. Nowadays, people are actually using pellets because you can actually reduce the one thermal cycle, right? For making a filament, so you need to actually prepare first pellets, and then you actually prepare the filament, and then use the filament putting inside the printer, and then you actually fuse it. So, but if you actually, if you don't want to prepare the filament, so you just want to use directly the pellets, right? So you can actually remove one thermal cycle or reduce one thermal cycle, as you know that. So if you go for a more number of thermal cycles, your properties actually will degrade, right? So if you could actually reduce one thermal cycle, I think that is you're saving it. Of course, there are cases where you will not be able to make filament, like example, very brittle materials. You don't want to add softeners, or you don't want to add any other material, but you want to actually prepare, say, sometime you also want to prepare simply a metals, right? There you don't have an option for adding another material, right? You cannot actually prepare solid filaments, right? So there you can simply go for a pellet, right? So and then you have different nozzle-based deposition, right? Example, you have a single nozzle, or you may be having multi-nozzle, or you may have the multiple filaments are actually coming into single nozzle, and then you are trying to extrude it. Or when it comes to pellets, you may be having a different pellets or different materials, and then you are actually trying to push through the different extruders, right? So and then what is the more important when it comes to the technology? The bonding between the layers, right? So that will actually make a huge difference when it comes to the technology, because here you are not actually using any lasers, where you are actually fusing or trying to help penetrating your previous layer, right? If you actually use a laser, right, you will be able to penetrate to the previous layer. But here, since you are actually using semi solid the layers when you actually extrude out of the through nozzle, so you need to make sure that the bonding between the layers are very important. So otherwise, it will simply will come out of it, right? So these are the three, major this thing. But if you see the configuration, right? Typical the FDM configuration, FDM machines are a material extrusion. So this is like you may have the filament, right? So you have the rollers, right? And then rollers are actually helping us to push the material towards nozzle. And this is actually the heated nozzle, right? And then if you actually see the closer look of the nozzle, where you have the fans, which will actually try to help when it comes to the fusing it. But before that, you have the heating area, right? So that, because as soon as the solid, the material or the solid filament is actually coming inside, so you need to actually melt it, right? Initially, this may be having standard the filament 1.75 is what the standard filament size comes in the standard form, right? But your nozzle is not like as, and if you actually try to print without heating it up, right? It will not happen, because you cannot actually bond the bond between the layers, right? Or you cannot actually bind them together, right? So what happens here? You need to make sure that it will print, go temperature, the material which actually melt, go for before after the melting point of respective material, and then you actually try to make semi liquid or semi solid in terms of the material. And then once you form, say example, typical PLA or ABS material, anywhere 180 to 230 degrees Celsius is what the typical the temperature wherein it starts melting of the filament, right? Once you achieve that, and then you try, since you're continuously actually pushing the material, right? So since this is actually liquid, by now it is formed in terms of liquid material. So as soon as you try to push the material, right? So now the liquid will actually try to escape. A liquid material will try to escape. So that is where you actually use a different nozzle size. You use a different in terms of, say example, you may be standard nozzle sizes are actually 4.5 or sorry, 0.45 or 0.2 mm the standard nozzles that you will actually find in the market. But and then sometimes, say example, you want to print more material, which is you want to actually increase the the printing speed, right? There you actually need to go for a bigger size of nozzle, right? So then you can actually, sometimes you may be having are mixing some powders, right? So there you may have to go for a little bigger nozzle also, and then you try to use it, and then make sure that it should not actually settle at the nozzle, otherwise it will actually clog. Most of the issues when it comes to the material extrusion, the nozzle actually will clog, right? If you see the 3D printer at your office or the lab, most of the time actually clogging will actually happen, because what happens, you may not have enough heat transfer through the nozzle, right? At the somewhere at the tip of the nozzle, your material will actually go on, will start accumulate, right? And it is mostly exposed to the environment. So then other that will again will create another problem. That's why you need to make sure you need to clear it regularly, so that you can actually keep clean the nozzle area, so that you can actually fuse it. And this is actually a single this thing when it comes to the nozzle. But imagine you also want to have a support structure to be printed within the same head, right? And this is actually the support structure, and then you have the model. Like you can actually use two extruders. One will actually go for a model, and then other will go for a support structure. But there are cases where without even support, having dedicated support nozzle, you can also use the same material for a support structure also. But and then you need to see how to differentiate right? Example, when you actually print a model material versus support material. What is the way? One way is you actually print with a less dense material, right? So less material so that you can actually, peel it off or remove it after, printing, right? So the typical, the major, if you see that system, right, of material extrusion, right? We have the extruder, and then you have art hand, and then you have the motions. So build platform, and then control electronics, and then which is basically, these today all these components are available, and then we have the dedicated website which is called RepRap, right? There, if you go there, you will get what kind of a extruder you want, and then what kind of a art end you want, and then what kind of a motion, and then what kind of a configuration that you want, and then what kind of a software that you can actually use it, so that you can actually make a full 3D printer. So the working principle, as I said, when you actually fuse the material, right? When you actually heat the material, right? So, and then since you are actually continuously pushing it, so once you actually liquefy the material, so and then you will actually try to escape it. So when as soon as the material actually will come, now that you need to actually convert into different shapes, right? So and then you actually make or form the different shapes and then solidify it. As soon as you actually lay the material, and then you quickly solidify the material, right? So since you have the sometimes support structure may be required. If it is example, this is simple part, you don't need any support structure. But imagine you have the material that you want to actually add on the top of this, but there is no support structure here. Otherwise, it will fall the material. So you need to actually have the support structure in this region, so that the material that you actually add it here, so will stay there, right? So example, if you see that, yeah. So if you see these two examples, right? If at all I want to actually build, right? So I need to have the support structure, right? Again, this support structure is also important. What kind of, how you are actually building the support structure, whether it is the fully solid support structure, or this is fully solid support structure. Say, or you want to actually have some kind of a bridges, right? So when you actually try to print some bridges, so you can actually save a lot of materials. But when you actually try to print here, what you are trying to do here is we are actually printing fully solid structure. But and then when you try to remove it, it will be difficult. But in this case, it is easy to remove. But the question is how you can handle before you actually start the model material, because they are the bridges. Now you need to actually form or form another layer which is before the after the bridge, before the model material, or before adding the model material, so that you can actually have enough support, right? So that is where you can actually build it. So example, sometime you may have different in terms of the materials. So you can actually also use different nozzles for making a different material deposition. Like example, you can add actually print two color material within the same nozzle. You can actually print, but and then you need to actually change the input material. But instead of that changing input material, why don't you actually have two separate with the two different colors, so that it is easy. At some time you can actually use a different color nozzle, and then you can actually have separate color components. So let me see if I can actually play this video.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer on a build platform. Thin, thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material on the preceding layers. The extrusion nozzle continues to move.
So here you can see this. So this is actually model material. But this complex structure, so without the printing support structure, you cannot actually make that complex structure. Otherwise, this material actually will fall, right? That is the one part. So other part is how to save this material, the support structure, right? By using a, you can use a, different, bridges kind of structure. What is this? This is how about now? Okay. So if you see that the structure, right, all the wireframe or bridges, then it will actually help to save the material. At the same time, you can actually print the model material.
While the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ulta, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
Okay, so that's about the technologies. I think working principle, I don't need to actually go into details because these are very common with respect to that material extrusion where you actually heat it up and then you use the X and Y stages, and then you can actually use a Z as a height. But of course, nowadays a lot of configurations are there, and then where you can actually use a different configuration. But if you see that most of the printers, so they actually use a bed to be moving X and Y, and then the head will be actually moving in Z direction. Right. So I think we have actually talked about the how slicing and then so on. These are the some of the the components that you can see that, like example, you want to have a color material, and then you can actually use two different in terms of the nozzle, or you want to have the color but you want to make sure you are have the two different nozzles, and then you only print that color with that model. So especially when you want to actually print large component, this will help. So, and similarly, you can see that sometimes you don't have the different material, but you have single material, right? So there you actually use a different density or different in terms of support structure, so that it is easy to remove, right? Here you have the two different material, right? It is easy to identify which is support structure and which is model material, so that you can actually remove the support structure after printing. So it is also easy to identify exactly. I have another video which is very interesting. So you can see it's a very closer look of how material being deposited. So can you tell me what are this? So are they good for the process point of view? Right? So they are actually going to make this part actually worse. Right? Now, if you see that this compared to this and this, you have more in this. But if you see this guy, when you try to push the material right from the top, right, somewhat it may not be 100% you are eliminating, but some of them actually going away, but still there may be somewhere trapped, right? So that's where your actual quality of the part actually will decide how much you are actually managing with this defects, right? So if you actually form like this, you will not get a good part. And then we found when you see that closer look, this is very common. This is even coming from the nozzle. This is where big air bubble is actually coming through the nozzle even after forming, and also it will based on the solidification, based on the environment temperature. So this will even further will create a bigger problem. Yeah. So this is actually the how and we need to actually question with this kind of air bubbles and this kind of defects, how you can actually see how to play the process parameters. Like example, if at all I want to decide what is the strength of the component or quality and then cost of the material or the cost of the printed parts. So what are the basically the parameters that we need to actually worry, right? So there are two parameters that will decide the quality and then strength and then cost of the component. One is the slicing parameter, other one is printing parameters. So what are the slicing parameters? So if you see that the slicing parameters are example layer thickness, right? So and you have the extrusion width and then infill density, infill orientation, infill pattern, and part orientation, support density, and then support orientation, right? And also few more parameters, example the cooling power, and then extruder temperature, the build plate temperature, and then you have the print speed. So these are the parameters that you can actually decide during slicing itself, right? So you can actually decide what is the layer thickness and what are the other parameters that you want to actually, or what is the overlap between the layers, right? Or what is the height of the each layer, right? So you are not actually deciding something later or during the printing. You are actually deciding before even you convert or before you actually transfer the file to the machine. Because whatever the file that you actually transfer, which consists of all these parameters, right? Because as I said, the parameters that you actually transfer to the machine are important when it comes to the quality of the component and when it comes to the strength of the component, right? How you can actually decide? It will decide basically you are actually controlling all the parameters during the slicing itself. During printing, before printing, you are actually transferring all the parameters so that you can actually maintain this the part qualities. Example, if I talk about the layer thickness or the width, right? So if you don't actually overlap with our previous layer, and then you may end up forming this kind of the gaps, right? And then you as also you add the layers. So this is the first layer that you have, and then this is second layer, and then this is third layer. So if you don't penetrate, or if you don't actually make the bonding between these two layers, and then when you actually try to test like in the z direction, that will be weak, right? And similarly, so if you don't overlap between this, right, when you actually try to pull the material from x and y, and then it will be like a weak in terms of the layer overlap, right? And then, as I said, you have the, when you go for a too close overlap, so which means you may actually add more material, right? Unnecessary, you actually reduce the speed of the printing, right? So that is another aspect, that where you need to have the optimal in terms of overlap also, right? You need to also have optimal in terms of the thickness also, because you may have better bonding when you actually maintain the smaller thickness, but and then you are simply reducing the speed of the printing, right? So but and then what is the basically the properties when you actually compare x and y versus z direction? Are they uniform in terms of properties, right? Or is it, what is variation that you have when it comes to when you compare x and y and z direction, right? And also when you actually print, what kind of a infill pattern, like example nowadays, right? A lot of them are actually exploring like how to reduce the material. Many times we don't need actually solid structures when it comes to the component, when it comes to that functionality, right? So there, how you can actually have the component, or you can have the material or the component, but and then can you actually save the material by only adding the material, or selectively, or you can actually use a different infill patterns. One is infill density, right? Another is infill patterns, right? You may have a different patterns, so that even if I apply the load from this side or this side, so I'll have the uniform in terms of properties. But I can also have that what is the overall density of the material, right? Can I have a 30%, or can I have 40%? That 40% also can be placed this side or this side or this side or anywhere. But can I have a uniformly distributed that 40%, right? So that's where you actually use a different infill patterns, so that uniformly you can actually distribute the material, right? Uniformly you can add the material, so that you don't need to worry about variation in the properties within the printed component. Imagine I have this material maybe 20%, I can as well add 20% towards the left alone. But and then when I actually test it something here on the right side, so I'll have different in terms of properties, right? So that's where we need to actually make sure how to maintain when you actually add the material in terms of properties. More importantly, how you can actually save the material by applying a different infill density and then the patterns, right? And similarly, you might have actually come across in terms of a support density, not just a support structure. One is, this is a model material that you want to actually print. So this is where you are actually printing a support structure, right? Because without this, you cannot actually print, because it is almost like 90-degree angle. Like before you actually start the printing, you will be able to actually print some extent up to maybe partially. You can actually extend a little bit of support structure that you actually you have already modeled material up to maybe here. But if you go further, material will simply fall. But you can actually take advantage of the layers of previous layers, where you can go extend your layers. Like example, you think about you have one layer like this, right? So another layer, if you want to actually extend without support structure, so you can actually build something like this, right? So now you are actually taking advantage of a previous layer, then you are actually laying other material, so that you can actually see how much angle that you can actually go without support structure, right? So this is actually how you actually take, especially think about something like this, right? You have the curvature, right? Here technically you don't need any support structure. If at all you want to go like this, even if you go like this, you don't need a support structure, because you are actually taking advantage of a previous layer. You are extending the deposition little bit, so that you can actually take the advantage of previous layer. So but that angle will not cross more than 35 degree when you actually draw vertically, right? But and then of course there are cases like where you can actually go beyond also. Sometimes people also tried going 50 or even 60 or so on. But and then you may have weak in terms of the material printed structure, right? But and then there are cases like we can actually, for example, this is a 45-degree that if I actually draw it, right, and then if I actually see how the support structure, you can, this is like if you change it, if you actually draw from bottom, and then you'll have different in terms of the support structure, right? So, but especially this kind of a support structure is, I mean, required. Sorry, for this kind of a model material, you need actually support structure, without which you cannot actually print. But of course, you can actually use the same model material to print the support structure as well. But and then since you are actually using the same properties for printing model and support structure, so when you try to peel it off, or when you actually try to remove the support structure, so here the layer you need to actually sacrifice, or when it comes to removing, right? So you have to see how much you can actually create a less dense material, so that you can actually remove the support structure easily, right? So similarly, you have the different in terms of part orientations. As I said, you can actually, and first then when you see that the component, you need to see that how to orient your component, right? So by simply orienting, you can actually save lot of time, lot of materials. Say example, if I have this component, right? So I can actually keep like this, I can keep like this, I can keep like this, I can also keep like this, I can keep like this. We always need to see how to reduce the height, because when if you see that typical motion, right? So x and y will not take much, but when it comes to the z, more the z height, more time you will be adding it, right? But if you see that if you add a material in x and y, because you are moving like this, the moment you actually stop it and then raise it, you are taking more time, right? That's why you need to see, always try to orient in x and y direction, more material in x and y direction, less material in z direction, because that will actually save your time, and then as well as the material. Of course, by saving the time, of course you can save many things, right? So but and then you have to question yourself, what are the basically the constraints that I have? What if I actually change it, what will happen? Because sometimes you need to have a better properties in x and y direction, right? Or you may be having better, you need to have better properties in y direction. You will not be able to actually compromise on that, right? You need to actually question, do I really need to actually vary the orientation, or is it okay, right? But and mostly that is the first fundamental concept in this case, is like we need to see how to minimize the height, so that you can actually reduce it. And you might have actually seen placing even one more part to the on the same bed, it will take less time than adding another part on the top of it, right? Because you are actually adding the, and then you can see a lot of infill orientations and infill density will also actually will play a major role when it comes to the printing of the materials, right? So this is just to give you examples. And then again, you may have process parameters, in example, cooling rate, and then build plate temperature, and then extruder temperature, print speed, and this again will also decide. These are not actually just the where you can actually decide your during slicing, but you can also actually see their effect during printing and then after printing. And then machine may not be actually giving you right temperature, although you might have actually set, but how you are actually ensuring the temperature of the build platform actually maintaining temperature that you actually set, especially when you have open models or open 3D printers, where usually you will not be able to control your temperature, right? There it will take different in terms of build this thing. And then you might have actually come across this problem, there's warpage, right? So especially at the corner, right? So the material actually will start coming away from the build platform, right? So this is called, especially, when you don't have enough the temperature onto the bed or the build platform, have the weak bonding. That will actually will happen when you don't have enough temperature to the bed, because say imagine this is actually room temperature, right? And then you are actually printing it, and then you have some temperature of the material that you are actually adding it, which means you're trying to bond or trying to peel away, or because you are actually trying to take away the material, right? Because and you don't have enough force or enough bonding or enough temperature to the bed, so due to which, and also especially if you see that the bed, right, they may not be actually having uniform in terms of the heat distribution, right? So when it comes to year and then year, and then you need to see that whether your bed temperature is actually the temperature of the bed is uniformly distributed or not. There you need to actually change the bed temperature, and as well as sometime also if you don't give enough for temperature for a fusing, right? So that also will actually will will start in warpage, because say you don't have you might not have actually given enough temperature so that it will actually will fuse the material. See, one is if you don't fuse it or if you don't liquefy, it will not go and stick to the bed, right? So because of which eventually it will come away. You need to have enough temperature, enough in terms of melting temperature, so that this guy will actually go and will stick to the bottom. So that is where the major mistakes I think many people will do. First 3 layers are very important when it comes to the technology. That's why you give more temperature when it comes to first 3 layers, so that later part you don't need to worry, because once you actually print the 3 first layers, and then it will actually will take care of the rest of the component, right? This is common mistake, everybody actually does this, right? Very common, especially in ABS, because they're very sensitive when it comes to the if you compare it to the PLA and all, right? So I think a lot of composite structures are nowadays people are exploring when it comes to the 3D printing, especially when you see that when you want to actually have a different like example carbon fibers or reinforced core, and then a lot of them are also even using short fibers and then long fibers for making the component. So you can actually have dedicated nozzle, right, for that, or you can prepare a filament with made up of a composite structure or composite materials, right? And that filament you can actually use for a fusing of the material, right? So as I said, there are different ways in which you can actually use fuse the carbon fibers. So and then you can have a different in terms of materials. So you can, as I said, you can use a single nozzle, and then you actually prepare the filament of a composite, right? Here you can see that the filament is actually, fiber is actually coming here, and then this is actually filament. So as the filament is actually going, the fiber is actually coming through this, and then you are actually combining, our filament is actually joining with the composite structure, right? And then here you can also see that other this thing where you can actually prepare the filament with the fibers, the composite fibers, and then you can actually make the composite structure. And you can have different other possibilities, like where you can actually print material A and material B or so on, right? So and then these are some of the components some of the researchers have actually explored printing of this using this technology. And then again, I think we have talked about Professor Ravi talked about a lot of magnetic materials. So here you can also actually prepare the magnetic filament, right, where you combine with PLA or nylon or so on, right? So and then you actually use the same way that how we actually fuse the material And then this is actually magnetic, the material, printed components, and then you can actually also have the controlled in terms of a magnetic field or so on, right? A lot of research is also actually happening in magnetic printing. So this is another the work that we have done it, like where you can actually print the magnetic material, and then you can also actually align the field so that you don't need to actually align after the printing, especially when it is semi liquid. It is easy to orient your field, right? You don't need to actually give extra when you need to give more field when it is a fully solid the structure compared to when you have the semi solid state, right? Here we try to orient during the deposition itself, so that we can typically traditionally they use a casting, and then later on you apply the field by putting this component inside the field, right? So this way you can actually save a lot of materials and time and all. So, and then nowadays you might have actually seen a lot of innovation is actually happening 3D concrete printing, right? So this is actually the same the technology that is actually used, which is basically material extrusion, right? So it is instead of you actually prepare the filament, so you simply use nozzle where you can actually prepare the different composition of cement and then different aggregates and then etc. And then you try to extrude the material. So a lot of research is actually happening in this area where people are actually printing the houses, and then you can also see some of the bridges. So especially when you actually have the gantry, kind of structure, or you can print a lot of this thing. Of course, you need to have that large gantry or large motion that size, so that you can actually print different the structures. So these are some of the examples. In fact, recently, this is actually L&T built 700 square feet in Kanchipuram, where you can see that the completely G+1 they have actually printed, and most recently you can see that in Bangalore, so they have actually printed the post office, right? So there you can actually find they have not taken the time and then much the like typical or conventional the time it takes like huge, but here they have actually used saved a lot of time and then materials, and then most importantly a lot of human involvement or resources that are actually required for building this kind of the structure. And a lot of bridges, right? Now they're printing a lot of bridges these days. So, and you can see that I think recently also there are some more examples which I don't have here. So they have printed north parts of India, especially where you want to actually you don't have access to resources, and then you don't have access to go and build the bridges, etc. So I think a lot of things are happening in the material metals also, because what is happening is when you actually prepare the filament with the metal, they also called a desktop metal 3D printer, where you actually use a small binder material like maybe 10% or 15%, and then you try to use that binding material for fusing it, right? And then later on you actually put it inside the furnace, so that you can actually remove the whatever the binding material, which is like maybe PLA or ABS or other material, right? And then there may be small reduction in terms of a material, but that can be minimized during preparation of the during the slicing time, right? So and then these are some of the components that you actually see, especially metal component. And recently we have seen a lot of other areas, like example you want to actually print some of the component for specific applications, including agriculture field or so on, right? These are just to give you some idea that what are the some of the applications that people are using it, right? So this is a website that I was talking about, where they call it as a RepRap, which is nothing but replicating rapid prototyper. This is actually started in 2005 by a senior lecturer at the University of Bath in UK. So this is like where anybody can actually go and then use all the material. You can design it. There are no patent. There are no copyrights that they have to worry, or one has to worry about making printers, right? This is actually the website. So if you go to visit, this is like another the Wikipedia website that you'll find all the, you can actually select the configuration. Like example, you want to have something configuration like this or like this, right? So you can actually there also you can find different configurations also. Like you have the models, and then once you visit, and then you need to select the configuration, different configurations like this. So and you will find a lot of them are also commercially available these days, right? And of course they're not specific to the company anymore. So you can always actually use if you want to actually build something like this, you want to build something like this. So completely you can actually build that at your home itself or at lab itself. So these are the some or the configuration. So we always tell this the joke, right? So you buy a one printer, and then you have the return policy, and then you make another printer, and then you give back the previous printer. But of course, but yeah, as I said, there are a lot of commercially available 3D printers in this segment. So starting from 15,000 or even less than this, I think you can make your own printer less than 10,000 rupees, and then anywhere if you go for other printers, like example industrial grade printers, Stratasys, and then flash 4s and so on. Right, these are the some of the printers that you will actually find. This is the example of initially you may be having the one printer, and then out of which you made a lot of components, and then you'll find another smaller printer which is like the child, right? So again, so as a researcher, there are a lot of areas that you, although the technology that traveled more than 40 years now, but when it comes to the research, when it comes to the areas that that I have listed here, are still a lot of work is actually required for making even more in terms of usage of the technology, right? As an example, as I mentioned, the interfacial bonding between the layers still challenging, right? How we can actually enhance, and a lot of porosities that I think you saw that one video that very closer look that you found, you might have actually seen a lot of porosities are actually creating during printing, and then even it is more if you just add any other next material, like example metals. Yeah. Possible. I think I have not checked it. I think it is may or may not be. It depends. Like what kind of yeah. But I have not seen per se that like rent it out. But that may be another business model. Yeah. No. That is at least I have not seen renting of 3D printers, but maybe that is a good business model that you can actually. Yeah. Yeah, but nowhere is actually like all the models that I've actually talked about, they will always fix the price. That if you see that, like even if you actually visit Amazon website, right, So you will find ranging printers ranging from 12,000 to. No, no, no. It is like basically what happens. Say you buy a printer, so you can actually print. You since you have all the dimensions of that printer, and you have all the components that are required. You know all the components that are actually required. Like example, the enclosure and then build platform and then the surrounding, everything that you know what are the dimensions. So you can actually print those parts using this printer. All that you need to actually buy the motors. All that you need to actually buy the or look after integrating all the motions, etc. So they will not give. You can actually make your own printer by using that printer. That's what I was talking. So and then you have that again still not many of them actually explored, especially refractory material printing and then their behaviors, and then a lot of research that gaps when it comes to that electric and then magnetic properties and then how the changes, and then as you know that one part of the technology is the flexibility in terms of design and then manufacturing. But how about the properties of when you actually print, especially magnetic and then electric properties, and then how to actually place fibers? I know it is easy to actually feed the fiber material, but can I actually orient fibers in different direction? Can I actually control the fibers? Right? How to make more controlled in terms of placing of the fibers? Right? Of course, already the cost of the machines have actually come down, but further can be reduced it, by especially when it comes to the powder or metal based. Still, the cost of the printers are high. How we can actually reduce it? Like example, where exactly the cost is actually involved, right? How to actually bring it down the cost of the machines, right? Since still we feel that the adapting of this technology is still not as anticipated like or expected a few years back, because of a lot of research is actually required to understand. Unless you have that a lot of the data and then data in terms of proving, industry may not actually come forward and then adapt. And of course, a lot of prototype things are actually happening, but when it comes to industrial scale, still the technology actually requires a lot of research, and then that's where, as a researcher, so we need to actually see how to improve in all this aspect, so that you can actually make a better in terms of a product and then quality of the product, right? So I think with this, I think we can stop. I have a few more, I think 2 minutes, but yeah, I'm happy to answer if you have any questions. Yeah, so multi-materials and then support structure, and then how to generate lines, and these are some of the areas that I think as a researchers that we should actually work on this for for quality of the product. Yeah, any questions? One is, you basically increase the temperature of the material or the nozzle temperature, so that you can actually improve the bonding between the layers. That is one. The second one is make sure your environment is controlled. Like make sure, like usually we keep anywhere 60 to 70 degrees Celsius environment maintained, so that there is a less the chance of or the temperature variation is less. In many cases, this actually problems happens when you have a temperature difference is large, right? So example, your printing temperature is say 100, but your surrounding temperature is 30 degrees Celsius. And then you obviously will see that huge temperature difference between the nozzle and then the bed, and then definitely your part may not go well. It will quickly solidify. Quickly it will just cure it off, right? So you need to have that controlled surrounding so that you get the quality of the part. That's why quality of the parts may not be possible, not that when it is possible, when you have the quality of the part when you have that open environment. Because even if you actually print good part today, but by evening you will not be able to actually have the same properties, because by evening you don't know what is the surrounding temperature, and by evening you don't know what kind of a condition, right? And then again you try tomorrow, then you will have different in terms of properties. That's why to keep it uniform in terms of the printing parameters and then this thing, you need to have the controlled environment. So one is controlled environment, and then controlling your process parameters, right? And then using the right material, right? And then as I said, you don't need to actually try to decrease too much. Otherwise, if you decrease too much, and then you will actually end up spending more time in printing, right? So yeah, there are few more other ways, but I think these are the major parameters that actually will affect your bonding between the layers. And of course, when you actually change the material, so again your bonding may have different, because you have different solidification or different the curing methods, and then yeah, that will also affect. Any other questions? Okay, so if there are no questions, I think we can stop here, and then we'll go for a tea. Thank you all.